Hello? Alright, so I'm going to go over the test 4 right here. Just question by question. Here's a broad overview. Then I'm just going to go through the question. Alright, number 1. 3 factors affect torque. What are the 3 factors that affect torque created by a force relative to the axis? And I said magnitude of torque, or the force really, the lever arm, or the length, and the angle applied. That is because torque is equal to the force times the lever arm times the angle. So angle applied, lever arm, length, and magnitude of the force. And I just kind of showed that there, put a little diagram of a circle, and like, oh, there's a force, there's a distance, and there is an angle. All right, question 2. Platform with rotational moment of inertia, I is equal to 40 40 kilograms per meter, and has a rigid object placed on top of it so that both things rotate coaxially, so on the same axis. If the combo has a net torque of 600 Newton meters and an angular acceleration of 6 radians per second squared, what is the rotational moment of inertia for the rigid object? So I kind of made a diagram of like axis going towards us, a block on top of block with inertia, moment of inertia for the bottom one, 40 kilograms per meter squared, and then has a net torque of 600 newtons with going at 6 radians per second squared. So I went 600 because torque is actually up here. Torque is equal to force times lever arm times the angle. So I said 600 Newton meters is equal to, oh, wait, sorry. That is for normal. This is for angular. More or less when you're messing with angular acceleration and moment of inertia, the equation works a bit differently. It actually is equal to torque is equal to the moment of inertia times the angular acceleration. So I pretty much said if this is net torque, 600 newtons, it's 40 of moment inertia times 6 radians per second. If they're both combined are moving the same, so it's 6 for the other plus the unknown. So you just move the numbers around, do the math, and you get 60 is equal to the moment inertia of the rigid, smaller I'm assuming smaller object. Or I said just X, so the placed on top object. Number 3, rigid object has a moment rotational inertia of I 65 kilograms per meter squared with frictionless axle. So I kind of put a diagram, it's a bit messy, but more or less it shows the object on the axis. I said X and Y is this way, counterclockwise is positive. We put the axis here, of course, 25 centimeters, 30 centimeters. The angle here is 60. The angle here is 60. And the force here is 250, this is 300. So, A, find the net torque on an object due to forces shown. Determine, and B, determine which forces, 1 or 2, this being 1, this being 2, could increase and how much in order for the object to get in mechanical equilibrium. So T1, I pretty much was like, hey, so what is the torque for each, right? So I went 250, torque 1 is 250 times 25 centimeters, so the force times that, the lever arm times the angle of application, which at this point it's being applied this way, and it's this angle right here, so it's 90 minus 60, so it's 30, which is equal to 31.25 newtons meters. Did it with this the second torque, which is 30, as it's the lever arm times 300, the force times sine of 60, as it is actually just 60 degrees going that way. it's being applied at an angle of 60 degrees from the where it would circle from. So, and I got 77.942286 Newton meters. If you get this one, which is counterclockwise, and then minus the clockwise one, you get a net torque of 46.6922864 Newton meters. So that's the answer to part A. And then part B is just finding X. So we pretty much say, hey, net torque is here, which is going to be equal, oh no, not net torque, sorry, this is the torque of 2. So the other one to even out has to be lever arm times the angle applied times whatever force, and that's the variable. So we just divide both sides by 2.5 sine of 30, and that gets us 623.58828 newtons is required for it to be in equilibrium on force 1. And that's the answer to part B. So question 4 is asking about the wind chime decor, and it hangs from a string. So pretty much the string holds a bar, and the bar on each side holds a string of a mass. The beam is fully angled at 25 degrees. The chimes each have a mass respectively of mass 1 being 0.25 kilograms and mass 2 being 0.35, and they're hung at either end. Find the masses, the main beam, if it is in equilibrium. So there's a lot I did with this. I think the first thing I wanted to do was say, okay, so the net torque, I'm going to actually skip and go ahead because I think it's going to be a lot clearer. So I pretty much was messing around. That was a lot of like figuring out what I wanted to do. I was trying to use the f of y and f of x, like the forces in the y direction and the forces in the x direction. That didn't quite work out. So I guess I didn't have application because I realized there's only one unknown. That is the mass of the bar itself, mass 3. So I got the torque and saying, hey, mass 1 is, because it also said that where it's hitting on the axis is 1/3 away from the left side. So 1/3 is mass 1 times its gravity, lever arm times mass, and it's all an angle of sine 25, right? And then we're looking for mass 3, which is a 6 because it pulls down in the center of mass, which is, it's a uniform bar. So 1/2 times 1/3, 1/6 times its mass times gravity, and of course sine. And then 2/3 times L, because the final one is 2/3 away from where it's being hung, and of course the same thing is equal to 0 because it's in equilibrium. So that is gravity times sine 25 times L. I just took this all out, very much like we saw in the Zoom meeting. It was just a lot easier and a lot more simpler, and I should just start doing it more instead of just inserting the values and multiplying, and then just it's equal to the same thing. So then we get 1/3 times 1/3 times 0.25 minus 1/6 mass 3 minus 2/3 0.35. Once you do all that, you just do the system of equations. You just equal to m3. That puts it to the mass of the third one is 0.902 kilograms. Now, I started to realize that's a bit heavy because you think about this is almost a full kilogram, right, on a wind chime. Wind chimes usually are hollow. Think about it because that's how they make the noise. So what I kind of put was that the bar being twice as heavy as the chime, more than twice than heavy as the chimes combined, and being about 2 pounds, I said that's a bit heavy, and that could be because it's solid. That could be because it is, maybe we're not accounting for some other forces, maybe because it's at an angle, we're not doing the right equation, and even that because And the only other thing I could think of is that because it's a wind chime, it's in the wind, and the wind is pushing down or doing something that is not put in the equation. Let's say it's like acting as a extra force down than just gravity or something of the other. Either way, that's my explanation for why it's so high. And then to the last problem, which is this one right here. This one is the warrior uses a ladder, leans a ladder, scaling ladder against a stone castle at an angle of 65 degrees. The coefficients of friction of the ladder in both the surfaces are given by the kinetic of 0.05 and the static of 0.3. I kind of discharged and didn't use the kinetic at all because if it's moving, then it destroys the question and it has no use. The question being, how far can the warrior climb at a mass of 95 kilograms before it starts to slide? Just for also context, the ladder has uniform density, is 3.25 meters long, and has a mass of 18 kilograms. So if we just show this kind of thing and show what we're working with, we have a lot of forces going on, natural, friction, friction as well. And then just over here, we have a lot of things pushing down. So I tried to do some stuff, right? But it wasn't working, at least in my head. So I just went, hey, the torque is equal to the friction of the wall, right? Going this way, if we're using X, Y, and counterclockwise, is positive. This is positive. The natural force of the wall, the natural force of the wall goes this way, and it's positive. The friction of the wall goes this way, meaning it's positive. The mass of the ladder, or like the weight of the ladder, goes this way, and therefore negative, and same with the guy, as G right there. Probably should have used W as warrior or something other. Either way, it doesn't matter. And then we also use the forces in the horizontal, which is only the force of the friction of the ground and the natural force of the wall, right? So you can equal them to each other, easy equation right there. And then pretty much doing this gives us a system of equations. I should have solved this, I think, symbolically before going out and doing this, but this is what I chose to do. And I don't think it affects my answer, it just would have made it easier for me to do it in the first place. Either way, we also have the vertical directions. We have the natural of the ground pushing up, plus the friction of the wall pushing up, and then the masses of everything else pushing down. So inserting values and rearranging. So this one right here can be rearranged to 1.3 as you just add these together, minus the everything here times together over x, minus this right here, which is 121.267. And then just solve for that. So divide everything by 4.3225. And that's because this is wrong actually here. I forgot that you're timesing both of these by 3.25 because you're also accounting for the distance they are. This is torque, so you're accounting for the distance of the lever arm. So that's something I had to consider there. But, and I was also kind of like, hey, they also point at a direction, right? That 90 or up, so they wouldn't their sign would just be 1. This I just reworded as like the start equation, and this we just equaled, we changed the friction of the ground to the natural of the ground times 0.3. So natural of the wall is equal over 0.3 is equal to the natural of the ground. So just inserting all of that into here, natural of the wall we have here over 0.3 as natural of the ground plus the friction of the wall. The friction of the wall is equal to just 0.3, the coefficient times the natural of the ground. So we just went 0.3 times natural of the ground minus everything else times out in the mass of the ladder and the mass of the guy, or the weight, is equal to negative 1108.53. going through the equation and just timesing everything by everything, we then try to isolate x, and doing so we get 0.1 meters, which doesn't seem right. So I was like thinking about it, and I thought of another way. Maybe if we just use two of these, because we only have one unknown here, technically, and just say the natural of the wall is equal to the friction of the ground, we can say, hey. So we can say friction of the wall is natural of the ground times the letter. And this time I was like, maybe I do account for it because it is, the system is going this way and you're pushing this way and it creates an angle no matter what. So I was like, okay, wait, if I go sine 65. So 0.3 times that times the lever arm times the angle. Same thing with the natural of the wall, which is just the natural of the wall is equal to the friction of the ground. So 0.3 times the natural of the ground. 0.3 times the natural of the ground, so times everything else, and then did the same thing for the L, and then had X as the unknown for the warrior. And I just redrew the diagram, and I also got F of Y as well. With this, we were able to say, hey, if we just times everything out as 91.53, because natural of the wall, we can add these together kind of thing. We can say that the natural of the wall, right, using this equation right here, or the natural of the ground, which this is just 0.09 natural of the ground, so 1.09 is equal to whatever these may be, which we did find, and we just inserted here. We can then say, if we just natural of the wall here, 0.09 times this times that times whatever this is equal to, which is like 1.09, which is equal to the weights right here divided by 1.09. And I didn't write that down. It's just algebra, but it is 91.35 plus 305.1. You get the answer for that as, you pretty much can get the answer for that, and then you just times this all around, right here, and we get an answer. I didn't care to write the entire thing down because I was just like, hey, let's get out some terms. So that's exactly what we did. Sorry, I'm getting a bit lost. There you go. I was like, we can take out a lot of the terms here. Mainly, right here, we can take out right here, actually, I was like, hey, here and here, both. More or less here. I was like, hey, we can take out a lot of these terms. Mainly, we can take out the sign, because everything here has the sign. Mainly, we can take out 3.25 and just divide this by 3.25. So that's exactly what I did, meaning I just had 3.3 times whatever number, and then there as well. I had the gravity times 9, right, because that just equals 9, 18 over 2, times 95 over 3.25 is equal to, and then, we just continued with this, multiplied it all out, and then here we just equal this, which is equal to 308.35 minus 286.759x, and we just solve for x, which is equal to 1.075. So that's answers to all the questions. I was having trouble using the different algorithms to like help me out. So a lot of this was just brute force, like trying to figure out. So I might try this again. This might be the only video, but hopefully I can get another attempt at all these and try to get it more refined. So yeah.